Okay, so I'm going to fill in a few gaps with this lecture, and I'm going to begin by talking about curves. It's a bit difficult to decide what order to present these topics in. I tend to present them in the order that I feel most comfortable with, but that's not necessarily the best pedagogical order, but I think curves is a great place to start, and then after that we'll do coordinate systems. We'll begin by doing the usual diagram, topological space, which is actually presented by the set and the topology, and we make it into a topological manifold by giving it an atlas. And then we will even promote it further, and this diagram should become very, very familiar to you. If you are comfortable with this subject, the diagram I'm drawing now is like, oh my God, he's drawing that thing again. There's no limit to how much you can draw this thing. But we're now going to draw the details of the atlas, and the atlas goes from the topological, for each chart, right? These are all the charts. So here's a chart V theta and a chart U gamma. The chart has the region and the mapping, and so this is gamma of U, and it goes to phi of V. That's what these little regions here are. And once this is guaranteed, all of this is guaranteed because we have a topological manifold. And then furthermore, I will take the intersection region and identify the location of the intersection regions as charted by each of the different charts. And then I will stipulate that the map between these intersection regions, there's two of them, that look like this, the composition of gamma inverse and phi, the composition of phi inverse gamma. Those maps exist, they're continuous. Again, that's all because we have a topological manifold. But then I declare that these two things have a different property. I say they have an additional property of being C infinity, or smooth, infinitely differentiable, therefore they are smooth. They're smooth, and therefore this becomes a smooth differentiable manifold. So that's the final promotion. The final promotion is we know these guys exist and are continuous, but we don't know that they're differentiable. And the reason we can talk about the differentiability is because they're going from Euclidean space to Euclidean space. So I have a multivariable functions here is what I'm dealing with, and I can take derivatives of those multivariable functions. That's not a hard thing to do. And if those derivatives exist, then I have a smooth differentiable manifold. And every time I talk about differentiability in this course, in this discussion of manifolds, you always immediately have to be thinking of, oh, we're talking about charting stuff from the manifold into Euclidean space, finding functions from one Euclidean space to another, and taking derivatives that we know how to do. Always think about that. So I can talk about, and I'm going to today, I'm going to talk about functions on the manifold. And then I'm going to say it's a differentiable function. I'm going to talk about functions between manifolds, and I'm going to say it's a differentiable function. But a function between manifolds, we can't immediately take a derivative. We can only take derivatives between charted functions. And so that's what we have to start thinking about. And the reason we know we can do it is because we're speculating, we're stipulating that we're dealing with differentiable manifolds, and therefore we can always move things over here and take derivatives. Okay, so that's where we're starting. So as a reminder, that's where we begin, and it's an important reminder because now I'm going to talk about curves. So we will begin by erasing all this and redrawing it, but now I'm going to redraw it, and I'm not necessarily going to immediately draw the chart maps, but we still have the same thing, x, tx, and an atlas. There's no symbol, by the way, for an atlas that is smooth, right? An atlas where all the charts are compatible, like we described in the last lecture. So I just provide an atlas, and the fact that it's compatible, there's no little symbol for it. So from now on, when you see an atlas, we're going to presume that it's smooth. And now I want to talk about a curve. So how would we begin to talk about a curve? Well, we got to just define what we mean by a curve. So I'm going to go to the real line. I'll give it a little 0 there to emphasize it. And I'm going to say that a point on the real line is given by lambda. That's sort of the parameter associated with the real line. So lambda will take on all the values on this real line. I could do this for an interval of the real line, and frequently it is done for an interval of the real line. Frequently it's done on, say, the open or closed interval, usually the closed interval from 0 to 1. You can do that too. Right now we won't worry too much about that. We'll just talk about the parameter lambda that's on the real line. And then I'm going to define a function, and I guess I'll, I'll call this function, I'll call it f for now. Why don't we just make it simple? This is a function f, and f is a function of the parameter lambda. So every point on the real line, f takes that point on the real line and maps it somewhere. Well, where does it map it to? Well, f of lambda takes the real numbers to the differentiable manifold x. So it's going to plot the real numbers to the differentiable manifold, and it's going to do so as a function of lambda. So f of lambda is an element of the differentiable manifold. And if we take all of the points in the differentiable manifold that are in the image of this real line, we're going to get some sort of labeling that should look like this. Well, we hope it looks like that. The fact that it's a kind of a connected curve and all these points are labeled, that has to do with its continuity and its differentiability. Now, as it lands in x, remember, it's going to land perhaps anywhere in x. You know, the function is right now kind of arbitrary. So it's going to go through all these different chart regions, right? So I'll just draw 2, but of course it goes through many. And this one might be U1, and this might, well, if I'm only going to deal with 2, I'm going to go with U and V, right? So it's going to go through these chart regions just like any other function might, or just like any other set of sets on the manifold, right? If I took any set on the manifold, right, say I took this set, open or closed or whatever, it's going to go through several different chart regions. In this case, it goes through U, right, and there's presumably another chart region here. So no matter how you do it, you're always going to end up going through multiple chart regions for any set that you lay down on this space. So let me undo those. So now this is a curve. This is a curve. This is how we are going to define a curve. It's a function from the real line into the topological manifold. And so remembering that the target of f of lambda is inside the manifold, we do have a problem that we want to kind of know the coordinates of this curve. We kind of want to know, we want to understand this curve. We want to be able to take derivatives, for example. That's going to be a huge problem. Curves are really critical in understanding the tangent spaces, which will be the next lecture. So we really have to get a beat on how these curves work. So normally in calculus we think of, curves are, what we're expecting is, I want coordinates a and b, f of lambda. Say this is say the dimension of x equals 2 just for concreteness. Of course, usually it equals d, right? But in this case, let's just say it's 2. But if it was d, it would be alpha 1, alpha 2, ... alpha, oh my God, really? Alpha d, right? That would equal f of lambda for a d-dimensional manifold. Whoops, f of lambda. Now, for right now, I'm just going to focus on 2, just to make things a little bit easier to manage for this demonstration. But we already know. If I'm talking about a pair of points, I'm talking about something in R2, right? So the manifold itself isn't R2, but of course it's a differentiable manifold, so we immediately push everything to R2 using the chart maps. So in the case of U, of this region, we use the chart map gamma. In the case of the V region, we can use the chart map phi. And now we're dealing with, because I've restricted it to R2, we can say the coordinates here are called x and y, and for this particular region here, for this little segment, I'm able to draw a curve in the Cartesian plane, say. And maybe perhaps For this other one, this is also, it maps through phi, and maybe that curve maps some weird way in r and theta, and say that curve does, I don't know, r is increasing, and I don't know, some curve in r and theta. Let me actually move it over to here, r and theta, like that. So the coordinates of this curve in any region where these charts are good, right? And presuming, in this case, you only see they're only good in limited regions, but you could also imagine bigger charts that cover most of the manifold, for example, like our sphere and the stereographic projection charts. Now you can assign to every point on this curve, you can assign coordinates, but notice the coordinates are over here. So this idea of AB equals f of lambda, that's not correct, right? This is incorrect. You're not going to get that. What does the actual replacement for that? The actual replacement, of course, is f composed with gamma of lambda. And this follows all the rules we talked about with composition. The domain of this composed function, the domain is the domain of the one on the right, and the range is the one on the left, which is over here. So this guy has coordinates in, well, I'll write it this way. It's an element of R2, right? And we can actually say AB equals. And, or for a given value of lambda, say lambda 0, right? So this is the thing that we have to always keep in mind when we're being sensitive about the presence of manifolds. We're really talking about the function from this real line into the manifold, but when we talk about the coordinates of the function, we're actually talking about this composition where we have this chart in there. Without that chart, it doesn't work. You don't have an AB. You don't have a system of coordinates that you can label these points with. So that's something to keep in mind. And of course, there's an exact parallel over down here, which is the composition of phi with lambda 0. And this is, of course, only valid if lambda 0 is inside this intersection, right? If it's inside the intersection of u and v. Otherwise, it would have to be some other value of lambda 0. And it will be a totally different set of coordinates, right? It'll be, I guess you could call it alpha 1 and alpha 2 or something. And there is going to be a relationship between these coordinates, and that relationship is obviously going to be very dependent on these transition functions, right? Transitioning from this set of coordinates to that set of coordinates. And that's going to be our next subject. So I'm kind of bleeding into the next topic of coordinates and how to understand coordinates a little bit better. But this is a curve. And once you have a curve, but what's important now before I move off of this, let's see, well, once I have a curve here, once I have this function, right, now I have an ordered pair that's a function of a real variable. I can use multivariable calculus and take the derivatives of this. So I can now talk about f prime. I can talk about the derivative of f with respect to lambda. However, when I do talk about the derivative of f with respect to lambda, I'm really talking about the derivative of this thing with respect to lambda. I'm talking about the derivative of the composition function of the chart map and the function itself with respect to lambda. Because remember, you can't take the derivative of something that lands in the manifold. You've got to take the derivatives between Euclidean spaces. And in this case, we start with a Euclidean space R, right? And we're going to a Euclidean space R squared. So you can take those derivatives. And we'll talk a little bit more about the multivariable chain rule later. But so when you see f prime of lambda, you've got to think this way. And that's confusing, because in a lot of books, they just kind of go through it very sloppily, not realizing that the range of f is not a space where a derivative can actually be taken. And you have to understand that they're doing a shorthand. And that's fine. You can do a shorthand, but it's confusing when you're first learning it. So I recommend when you first learn it, you see things like this, you really study it. What's the actual meaning of f? They might just be willing to rename this thing f, right? Say, let's just cut out the middleman, which is gamma in this case, and just call it F. And that's all right. But understand what's actually going on. You're actually going into the manifold and then out of the manifold into this Euclidean space. And when you take the derivative, you're taking a derivative here, a derivative from the Euclidean space, this total mapping, which is F composed with gamma. All right? Okay, so now we're going to talk about something else. In particular, we're going to talk about coordinates. So again, I get to draw this very same picture. And I will talk about one region. Well, actually, you know what? This whole thing is I'm just going to talk about a region U. So a region U, so U gamma is an element of the atlas of our differentiable manifold. And the differentiable manifold is X with its topology and its atlas. All right? And so gamma will move into, and for the purposes of this, I'll talk about R2 again. And of course, whenever I talk about R2, I'm talking about R2 with its usual topology. And the reason we have its usual topology there is because that's what it takes for us to do calculus. You don't, if you're arriving here without having taken a course in topology, which is almost certainly the case unless you're actually studying mathematics, you don't quite realize it, but all of your calculus was dependent on the topology, the usual topological structure of R2, which involves these open balls, right? And the epsilon delta proofs associated with calculus. Some of you have seen epsilon delta proofs for limits, but all of that stuff, all of the epsilon delta proofs, all depend on the usual topology of R2. So once we have this, and we say we call this X and Y here, and we have our function gamma that takes us, our chart function gamma. Now I should think carefully a little bit about gamma. How is gamma constructed? Well, gamma of a point P, it's a set of points, a D-tuple, which in this case I'm just calling AB because I'm D times here, right? So D, if D equals 2, I guess is what I should be saying. If D equals 2, it implies you got a kind of AB here. But if it's a D-tuple, but these guys in here are actually functions of P. I should probably think of it this way. Why don't I think of it as alpha 1 of P, where alpha 1 is a function, and alpha 2 of P, where alpha 2 is a function. And now I have what are called coordinate functions. These are the coordinate functions. And these coordinate functions, if you look at them closely, if I have a point P here, alpha 1 of P, that only goes to R, right? It's gamma is the thing that kind of collects them all together and creates the ordered pair that takes you into RD, which in this case is R2. So, but each slot, clearly you have to be able to identify the value of each. If you're going to ultimately make a D-tuple, you're going to have to be able to calculate each of the members of the tuple. Those functions which do those calculations are called coordinate functions. Coordinate functions. And the reason coordinate functions are important to talk about now is because they show up almost in all elementary general relativity books, and I presume that many of you have read a lot of these books. And I kind of want to make some contact with those books. So in those books, what you'll usually see is something that looks like this. You'll see something that's written x prime, which would mean the x coordinate. Well, let's say it would be something like x0 prime, x1 prime, x2 prime, and x3 prime. Those are the new coordinates. They are functions of the old coordinates. So x0 prime of x0, x1, x2, and x3. And that would often be written as, well, then likewise for this one, x1 prime, x2 prime, x3 prime, where they're functions of these etc., etc. So this, the way they write this is, or the way they say this is, the new coordinates are functions of the old coordinates, right? So now we understand, when we understand chart maps, we're actually dealing with one coordinate set system here is one chart into a coordinate system, and we're dealing with the fact that there's going to be another chart, V, and this intersection region, right? You can only have new and old coordinates on a region that intersects, right? And I'll take out this alpha for here so I have some room. And of course, this guy is going to have its own map to its own coordinates system, R2. And these regions here are going to have their transitions, right? In this case, it would be phi inverse composed with gamma. So, so what we're talking about here is the new coordinates is one of these is called the new and one of these is called the old, and the transition is the changing the relationship from new to old. However, this transition function takes a d-tuple from this Euclidean space and gives you a d-tuple in this Euclidean space. But that's not how elementary textbooks go. Elementary textbooks say, no, one coordinate, which is a real number, is a function of all the, one new coordinate is a function of all the old coordinates. One new coordinate is a function of all the old coordinates. One new coordinate is a function of all the old coordinate. So how is that supposed to actually look? Well, it's actually not very difficult to understand when you look at it in terms of this sort of mapping. All right, so now I'm going to redraw this a little bit cleaner so we can go through this a bit stepwise. I tried to do it on the fly a moment ago and didn't work out so well, so I'm going to redraw it. Okay, so this is my new chart. It's sort of cleaned up a little bit, but what I've done is I've kind of drawn very carefully the region U and the region V, the chart regions on the original manifold, which is over here, and I've projected through the chart map gamma onto R2, so you see the intersection region here, and also through the chart map phi, and you see the region over here. The chart map gamma is defined through its two coordinate functions, and I call them x0 of p and x1 of p. So I'm now leaning into the general relativity kind of notation where the first coordinate is subscripted with a 0. A totally superficial change, but I do want to make contact with this sort of general relativity textbook type of notation where you have the new coordinates are functions of the old coordinates, right? And I want to explain how this thing emerges from this architecture of a differentiable manifold. And it's actually dependent on a differentiable manifold, right? You can't do this without that. And phi, instead of calling these things alphas and betas, I'm going to stick with the GR notation. Phi will be the prime coordinate system where its coordinate functions are x0 prime and x1 prime. And of course I've taken our d-tuple down to just 2, just for the sake of making it a bit tighter. Oh, so the d-tuple's down to 2 over here, but notice I've got 4 over here. Yeah, that's a mistake, right? If the d-tuple's 2, it's only going to be 2 everywhere. Okay, so let me cut it back. Now, so what the point of all this is, what is this thing? How do we write it in terms of our charts and everything else? Well, the new coordinate down here is a function of the old coordinate. So what is this old coordinate? Well, this old coordinate is the point over here in the Euclidean space that's mapped through gamma, because we're calling the old coordinates the chart driven by U and gamma, and we're arbitrarily calling the new coordinates by V theta. So this guy here, that ordered pair, is connected to gamma of the point P in the manifold, right? Some point P in the manifold in the intersection of UV. P has to be in here somewhere. So that's what this guy here is. Then what is this guy? Well, that guy is the one dimension. It's going to be the function that takes this ordered pair and returns a real number, which is just the x0 prime coordinate, the coordinate in the new system. So we take the point that we take the point here, which is gamma p. We bring it back to the manifold, which is using gamma inverse. And then we're not going to push it here, because if we pushed it here using phi, we would end up with an ordered pair, right? Remember, phi is going to give us an ordered pair in the new system. But we don't want an ordered pair. We just want a single real number. So instead of using phi, we just use the coordinate function associated with phi, in this case x0 of p. So this guy here is this whole process. It starts here and it ends up here. So it's got to be gamma inverse composed with x0. So this guy here is gamma inverse composed with x0 prime. That's what this function is. And of course it operates on gamma of p, which is the ordered pair x0, x0, x1. So this is the old coordinate, this is the new function, and ultimately this equals a number which we typically redundantly write as just x0 prime. So this name x0 prime in elementary GR textbooks serves as both the value of the coordinate, but also when it's given arguments it serves as the coordinate function. But understand, this coordinate function is this thing here. It is the inverse mapping for one chart, and we know the inverse mapping exists by definition. By the fact that we have a differentiable manifold, we know that inverse mapping exists. It's that inverse mapping followed by the direct mapping of the coordinate function. And that's where these expressions come in elementary GR. Likewise, the other one, of course, is x1 prime equals x1 prime of x0 and x1. And that, of course, in this case, x1 prime is related to x1 prime, the coordinate function, composed with gamma inverse. And you can write this the other way. You can write the old coordinates are functions of the new coordinates by writing x0 equals x0 composed with phi inverse, right? And that will take as an argument phi of p, which is a ordered pair over here. So this is the connection between these general relativity textbooks and our new understanding of manifolds. The thing is you have to, once you know this, you've got to almost always in your mind understand and make this little substitution in your head. It's almost easier not to understand this, and indeed that's why a lot of general relativity textbooks don't really go into a lot of detail here. But once you understand this, you've got to kind of say, okay, what's the chart? How are we making these points? How are we plotting these points? How are we developing these ordered pairs? And as you'll see when we talk about tangent spaces and we fully develop the concept of tangent space, not like the hand-waving argument I made in the what is a tensor lectures, when we really go into what it is, it's critical to keep this in mind because everything is chart dependent. Everything depends on our choice of charts. And now you're kind of being able to see these choice of charts are quite arbitrary. We could change our atlas up and we can make these charts totally different. But what's going on in that manifold shouldn't change if we just change our charts. But ultimately, the only reason all of this is possible is because we have an atlas on our manifold. That atlas maps everything to a place where we can do calculus. And ultimately, these functions here are exactly the kind of functions we want. They're functions of ordered pairs of real numbers to the real numbers. Or if we leave it just in terms of the transition functions, if we want to take these more kind of complicated entities, gamma inverse composed with, or phi inverse composed with gamma, or likewise phi composed with gamma inverse, these take ordered pairs to ordered pairs, but you can still do multivariable calculus on those things also. The point is ultimately you see how we struggle to get everything in terms of Euclidean domain and ranges in Euclidean space. And the only reason that's possible is because of this manifold construction. Okay, so enough about that. I do suppose there's another way of understanding coordinate systems too that I guess I should just quickly show on one chart. So this is one chart with its chart gamma. If I go to the real numbers here and I call this x, I go to the Euclidean space. In Euclidean space, this will be R2 with the usual topology on R2. And say I draw these lines of constant values of x, I can take gamma inverse and I can project those lines of constant value of x. I can label these points on U with these various lines of constant values of x. Likewise, I can do this for y. I can take lines over here of constant value of y, and using gamma inverse, I can project those and label the points over here based on those constant values of y. So a point P, well, I guess I should change the color for P. A point P will be labeled, literally labeled through this mapping and inverse mapping. I guess I could put point P over here. Well, that would be gamma P, right? So gamma P lands over here, and where it lands, it gets its ordered pair, and I can actually like put that ordered pair over here and label these points in this manifold with the coordinates that are assigned through gamma. So gamma assigns these coordinates, and then I look over here and I kind of write these coordinates down, and the locus of the guys who all have the same value of A are the black lines, and the locus of guys who have the same value of B are these red lines. And I can kind of think of myself as taking this Cartesian system, or this system here, this x and y, and kind of putting it on top of the manifold. And then that's a picture you always see in generally textbooks when you look at these curvy linear lines. What you're really doing is they're projecting backwards through the chart map, and they lay it down on top of the manifold. And then, of course, obviously, sort of goes without saying, you can do this again, and I can call this r and theta. Actually, it's usually a small r, right? Small r and theta. In this other chart mapping, I could, for the same region or for some part of significantly overlapping some other region V, and I could take all of those things of constant r, and perhaps if I did that, what did I just do? Sorry about that flash there. But if I did that, and if I map this under the inverse mapping, these lines might end up looking something like, if I labeled all those locus of points, I might end up with something like this. You know, the locus of these constant r's, and maybe if I did the thetas, you know, the constant thetas, I might end up with something like that. And remember, these are just labels now. The points over here, I'm just kind of suggesting polar coordinates for this, and I'm suggesting rectilinear coordinates for this. But over here, it's just labeling of the points where they would land if they were mapped through their respective mapping over here. I just take those numbers and I kind of put a little flag up and label them, and I get some suggestion of the coordinate system over here. But now you can kind of understand how, if I take a region over here, U, with another chart here, V, you know, if V is working through phi, you know, if this map is from V to here, this overlap region, although I've kind of expressed the overlap region already as, let me be a little more careful. If there are these two different mappings that work for you, this mapping here becomes the coordinate change. And that's what we've already been talking about. And I can express it in the multivariable form like this, or I can express it in the coordinate form where I'm doing things like x0 prime composed with one of the other chart functions, say gamma, or I think it would be phi, the way I had it defined in the last screen. But either way, this is how coordinate systems are sort of laid down on your manifold. This is the construction that does it. It's these lines of constant values of these functions being pushed back by the inverse of the mappings. And that's all that's going on. So that's how these coordinate changes, these transition functions, are related to coordinate changes. And that was sort of the point of this segment of my talk. All right, now the one last thing I want to show is just another sort of demonstration of how we talk about smoothness in terms of these maps and charts. And now I'm going to take two different manifolds, X, Tx with atlas A, and Y, Ty with atlas B. And these are two different differentiable manifolds. So they have all of the structure we've talked about. So, and it makes perfect sense for me to just quickly and schematically draw these little pictures, and to draw these little pictures here, where I'm now very quickly saying all the stuff I said before, right? I have chart regions, chart maps, regions in Euclidean space. And the same is true over here. I have chart regions, chart maps, and those regions map into Euclidean space. All of the stuff we talked about exists for this, and we're going to be, they're smooth differentiable manifolds. So now I speculate, well, I can have a function from one manifold to the other, right, called f. And f is a function that takes points in x and gives you points in y. And now I can ask the question, is f a differentiable function? Right? But I can't talk about taking derivatives of f directly, right? That's because its domain and range are both in complex topological spaces, ty and ty, where such a definition might be very difficult to come up with. But I can take derivatives between Euclidean spaces, right? So now instead of talking about the differentiability this way, which is what defined the transition functions, I'm going to talk about differentiability here, which would have something to say about the differentiability of f. Well, how do I get from here to here? Well, it's actually, by now, should be painfully obvious. If gamma is the chart map for u, and phi is this chart map for v over here, well, to get from here to here, I'm going to take gamma inverse, compose it with f, and then compose that with phi. Right? Gamma inverse composed with f, composed with phi. And once I've done that, this guy is a map between RD to R, say, B, right? Where this dimension, the dimension of y is equal to b, and the dimension of x is equal to d. So now I can talk about the differentiability of this guy, because this guy is going from Euclidean space to Euclidean space. And likewise, this guy here too, right? It's the same thing. In the intersection, they both better be differentiable in the intersection for sure. But if it's differentiable everywhere, then f is called a smooth differentiable function between the two manifolds. A smooth differentiable function from this guy to this guy. And as such, once again, we see that in order to understand the differentiability of functions involving the manifold, just like we did with the curves, we have to lean on all of our manifold structure. We have to lean on the charts, we have to lean on the chart maps, the chart regions, the chart maps, which is the charts. The function itself is sort of hidden in between the two, and the other chart region, the other chart map. And then we, again, take our different derivatives in Euclidean space. And then one other important thing about this. Just because f is differentiable doesn't mean it's one-to-one, and doesn't mean necessarily that it's on-to. However, if f is also one-to-one and on-to, by the way, that's called bijective. It's if f is a bijection, if it's 1 to 1 and onto, and the inverse of f is differentiable, if the f inverse is also differentiable in the same way, in the same way as f is, so if I have f inverse, which is a map from y to x, well, if f inverse is differentiable in the same way down here, where I'm now dealing with phi inverse f inverse phi, see, wait a minute, let me get this right. It's not down here, right? It's up here. Up here it would be phi inverse acting first, this way, then f inverse acting second, which is this thing, and then gamma acting last, like that. So if that guy, which is a map from RB to RD, if that map is differentiable, so now, if this map is differentiable, if this map is a bijection, which will flow to this guy, so we have bijection, differentiable. It's basically everything in a homeomorphism and differentiability. I guess that's the way to say it. It's a 1 to 1 onto with an inverse that is also continuous. So it's continuous 1 to 1 onto with a continuous inverse. You replace the word continuous with differentiable and differentiable inverse, which of course implies continuity. And this thing is just like a homeomorphism, but it's only applicable between differentiable manifolds because the concept of differentiability only exists for differentiable manifolds. So this is sort of like it is a homeomorphism because differentiability and continuity go together, but it's more than that because it's differentiable, whereas a homeomorphism between topological spaces is only continuous in both directions. F and F inverse is continuous. But if for differentiable manifolds, it could also be differentiable, and if that's the case, we have that was a lot of words to get to. We have two diffeomorphic spaces. That means another way of saying it is that these two spaces are diffeomorphic. If a function exists, right? If such a function exists, the property of being diffeomorphic is an absolute property. I may not know what this function is. That doesn't stop the spaces from being diffeomorphic if the function exists. If I know it exists and I'm dealing with a different function, they're diffeomorphic if a function like that exists at all. So the question of whether two spaces are diffeomorphic involves either constructing such a function or some other proof that gets around with that, that proves that that function exists even if you can't construct it. But diffeomorphisms is the homeomorphism for differentiable manifolds. Okay, so we have talked about, today we talked about curves. Curves which were functions from the real line into the manifold, and we also made sure we understood that that was to be projected through the chart mapping into RD. So the curve comes from the real line, goes into the manifold, goes into RD. And now we can understand that the coordinates of these points, I can actually take the x-coordinates of these points. If I understand gamma to be x0 of p and x1 of p, right, I can now talk about the x-coordinates of points on the curve using that x0 composed with f, say. And we're going to use this a lot in our next lecture. We're going to use this concept a lot because next lecture is about tangent spaces, and we're going to formally get into tangent spaces, and we're going to see how it's related to the idea of curves. So we talked about curves, we talked about coordinate systems, right? We talked about diffeomorphisms. I feel like we talked about one other thing. But no, I think actually that is it. So the next lecture, we are going to talk about tangent spaces. And that is sort of where we really take off with this and really make connections between the subject of manifolds and the other lecture, what is a tensor. We have to get the tangent spaces down and we can start making those connections. And we will heavily involve ourselves with the understanding of curves when we do this. Okay, I'll see you next time.